Thank
you very much. And good morning, everyone. It's my pleasure to be here, and thank you to the MBRC for the kind invitation. So, do you see my screen correctly, I guess?
Yeah, it is.
Okay, perfect. So, as it has been said, the title of this presentation is Soil Moisture Mapping using L1 Microwave Radiometry and GNSS-R and Disaggregation Algorithms for High-Resolution Application. And I'm with the Technical University of Catalonia in Barcelona, Spain, with the Institute of Space Studies in Catalonia as well. And for the past 2 years, I've been an aspired visiting international professor at the UAU in Alain. A second. So the outline of this presentation is the following. First, I will make an introduction of our lab, basically what we do at the Remote Sensing Lab within the Department of Signal Theory and Communications at the School of Telecommunications Engineering at UPC. And then I will make an overview of soil moisture remote sensing, because before we were able to measure remote sensing, to measure soil moisture from space, there were a number of techniques that were used, okay, NDVI and others. And I would like also to comment on that, because actually they are sensing other things and not particularly soil moisture. But I mean, they were used for many years as proxies for soil moisture. Then how to measure soil moisture using microwave radiometry, which is known to be the most precise technique to measure the soil moisture in the surface. But the problem is that the resolution is very coarse. So I will explain how to go from these coarse resolution maps into high resolution maps by combining it with other sources of information. Then I will explain how to obtain soil moisture using GNSS reflectometry, which is one of the newest techniques, even though it has been around for more than 25 years already. The big boom of GNSS-R has been in the past 5 to 10 years. And then I want to take advantage of this audience, okay, to explain a few other things that can be done using GNSS signals of opportunity, but now not in reflection, but using them as transmission, okay? As they pass through the vegetation, they also get properties from the vegetation, and this can be used to measure the vegetation optical depth, which is related to the vegetation water content. And then I will comment a little bit how we are applying all these into a project that is called AI for Water. We are conducting, this is our last third year that we are starting now. And it's basically to create a digital twin in some agricultural fields to optimize the water resources. And then I will finalize with some conclusions. So the UPC Remote Sensing Lab. We are physically based in the School of Telecommunications Engineering in Barcelona, in the north east of Spain, and we are part of what is called the ComSense Lab, okay, which is basically a group focused in communications and remote sensing. And it includes a team working on antennas and radio systems, microwave systems, free space optical communications. And then over the past, since the year 1990, mostly, all the activities related to remote sensing have really taken off, and are nowadays, they occupy more than half of the activities of the group. We have 3 subgroups: active microwave remote sensing, passive microwave remote sensing, optical remote sensing, notably LiDAR for atmospheric applications, and the NanoSat lab, in which basically we test some of the new sensors that we have been developed. We are about 25 faculty, plus postdocs, PhD students, and master students. So basically, one of the particularities that we have in our group is that we go from the instrument developers as telecommunications engineers. Basically, we apply all the techniques that we know for communications, antennas, amplifiers, filters, mixers, and so on, and all the signal processing techniques. Okay, we apply all these to develop instruments, and then we go all the way down to the applications. I'm going to go quickly through some of the type of instruments that we have been developing in the passive microwave group. Okay, and basically, I will start with Laura. Laura is the L1 automatic radiometer that we developed in the year 2000. in preparation for all the ESA-SMOS activities. It was the first fully polarimetric L-band radiometer measuring the 4 Stokes parameters, and it was used in experiments in an oil rig to measure the emissivity of the ocean, including all the effects, including the rain as it splashes in the ocean, over land, etc. POW real aperture radiometer, RA, was also, to my knowledge, the first one, including digital beamforming and beam steering for a microwave radiometer, techniques that were used in communications before, but to my knowledge, not before in the field of passive microwave. And then Mary-Chain, which is the multi-frequency experimental radiometer. Okay, it has a number of bands covering from L-band into WB band at 1800 GHz. Basically, all the bands that are used for microwave radiometry, and we put them in a track, and we can go for experiments. We also develop smaller instruments. So this is like Ariel, a small version for a plane. This plane is from the Cartographic Institute in Catalonia. And here you have an example of the techniques that I will be presenting later. The native resolution, so this is 2 strips made with the plane. So this radiometer only has 1 beam looking into the nadir direction. And as the plane make 2 passes, okay, we had a very, very coarse resolution on the order of 200 meters because the antenna has a limited size. As you can see here is about half a meter, or actually a limit, something less like 40 centimeters. And the pixel size was about 200 meters. But combining this information, the microwave radiometry information at L-band, together with multispectral imagery with TASI and CASI, so in the visible near infrared and in the thermal infrared as well, we were able to downscale down to 2 meters. And here you have another example in Salamanca over the Remedus test site that was used for the Calval of SMOS, ESA-SMOS mission. Other instruments that we have developed in the field now of GNSS reflectometry. In the year 2001, we developed the first ad hoc instrument for GNSS reflectometry in Europe. At that time, there was only one sort of prototype that ESA, the European Space Agency, was using, that basically consisted in 2 recorders of GNSS signals, one for the up-looking signal, the other for the down-looking signal, but on tapes and not even synchronized digitally, but they were doing actually manually. So it was really, really painful. A few years later, and thanks to the ERC, European Young Investigator Award, we developed the first GNSS-R instrument that was able to compute the delayed Doppler maps in real time. And what you see here, actually it's a slowed down version, because each of these photograms corresponds to a 1 millisecond of data. Okay, this is in a cliff in the Canary Islands. And by the year 2008, we already have a spaceborne prototype, okay, for INTA Microsat 1, but unfortunately, due to the economic crisis, that mission was cancelled. We have developed other type of instruments for ground-based applications, for, here you see for a rover. We also developed for a plane. This plane is from Professor Gerald Walker in Australia, in Monash University, and this is the most sophisticated instrument that we developed with 19 elements looking in the array, looking up, looking down, other 19 elements, 4 beams, 2 bands, and basically all the beamforming was taking into account the attitude of the plane in order to pick the direct and the reflected signals. And we also developed instruments for CubeSats, and this is the first one, CubeSat 2, in which we put a GNSS reflectometer. And as I said, we also try our instrument. That is how I started the UPC NanoSat Lab, because we wanted to test some of these instruments in real spaceborne missions. So we have basically a very small lab, okay, where we have enough testing facilities to do all the vibration test, thermal vacuum test, attitude control test for our CubeSats, and we have a ground station. Here you don't see, but there is another UHF VHF antenna here, and this is the S-band dish, okay, from where we control and download the data for the different missions in which we have been involved since we started in the year 2007. And here's CubeSat 1, CubeSat 2 that I just mentioned for GNSS-R, CubeSat 3 that was cancelled because of the crisis, as well CubeSat 4 that was recently launched in the Ariane 6 maiden flight, FSSCAT mission, the first Copernicus mission, the first CubeSat mission contributing to the Copernicus system. And I want to also highlight these 2 because in these two we have hosted payloads in satellites that are from NSSTC in the UAE. And this is our upcoming mission, another 6U satellite, but this is for ionospheric research. So, because this talk is about soil moisture, okay, I want to present you, I mean, as a teaser of what will be coming next, some of the results in one slide of the FSSCAT mission. They said FSSCAT has two satellites. This one here, CubeSat 5A, has includes the payload FMPL2, which includes it's on the other side. Here is an Earth view and 6-patch array at 2 bands. 1.4 for microwave radiometry, 1.57 for the GNSS reflectometer. And here you can see the up-looking antenna. The other of the 6U CubeSats contains a Hyper Scout 2, which is an hyperspectral imager that contains bands in the visible and near infrared and also in the thermal infrared. And as you can see, later that was kind of the culmination, because we were able to put everything together, everything that we had been doing over the past 20 years, okay, in a CubeSat mission. And we were able to obtain, these are real maps obtained from this mission. This is soil moisture maps in the Northern Hemisphere. You see as time passes. Okay, same thing with GNSS-R. But in GNSS-R, as we'll be seeing later, we only see the mapping is less dense because we only see the tracks where the specular reflection points take place. And then here are some figures of merit of the quality of the results that we were obtaining. A little bit worse than SMOS is a SMOS or SMAP, but for being a CubeSat mission of just a small fraction of the price, etc. I mean, it was actually pretty close. In SMOS and SMAP, they are on the order of 0.04 or 6, and here we were just 50% larger. So let's start with an overview of different techniques that have been used and are used to measure soil moisture. First, okay, I will put here the NDVI because I have seen many people that use NDVI to infer or to see if the soil is wet or dry. But actually, I want to highlight that this is not a measure of soil moisture. Many people use NDVI because it's readily available. And, you know, there are applications that even the farmers can find in their phones, and they see, well, this part is more irrigated, this other is drier, so I need to irrigate more here than in there. But NDVI is not a measure of soil moisture. NDVI is a measure of the vegetation state. It measures the reflectivity in the red, in the near infrared, and by taking the difference divided by the sum of these two reflectivities, you get a number that goes from 0 to 1 for the vegetation, okay, saying that if it is 0, basically, or tending to 0, or very low value, the vegetation is not healthy, but as this number becomes large, the vegetation is healthier, okay? And nowadays we have several missions that can provide this value with very high revisit time and good spatial resolution down to 20 meters. Also, in the field of soil moisture, when we lack of microwave sensors, people use the apparent thermal inertia or this triangle. Okay, this triangle, basically what you have on the x-axis is the NDVI that I just commented in the previous slide, and the land surface temperature or LST. So the LST is measured, okay, in this part of the spectrum, around 10 microns. Okay, and the NDVI is measured from the reflectivity in the red and in the near infrared. Okay, and basically in this triangle, okay, what you can see is that when the NDVI reaches the minimum value, it means that actually the vegetation is dry. Okay, it's not healthy and it's dry because there is a lack of soil moisture. The specific heat, the water has a large specific heat. Okay, so when there is less amount of water, the temperature goes during the daytime much higher, and then during the nighttime to a much lower value. So the temperature excursion is much larger than when the NDVI is high, because there is a lot of water. When there is lots of water, the specific heat it's higher, so the temperature excursion in the soil it doesn't go that high during the day and it doesn't go that low during the night. So the temperature excursion is smaller. So actually, okay, through these formulas, people get an proxy of the amount of soil moisture on the ground. Okay. Unfortunately, this doesn't work, for example, if it is cloud cover or in days when the different temperature difference between maximum and minimum is less than about 3 degrees. Okay, so it only works in some conditions. Again, this method was developed, or I have seen it since the 90s, and it worked relatively well, except in these conditions and in the absence of other techniques that are more performant. We have also seen ways to, again, it's not really the soil moisture, but I want to emphasize it's a soil moisture index, okay? But also on the tops of the surface. This number as an index goes from 0 to 1, so sometimes it's even more misleading than the previous one, because also the soil moisture, okay, as cubic meters of water per cubic meters of volume, it also goes from 0 to 1. Actually, in real soil, it will go from 0, when it is absolutely dry, up to 0.4, in some cases a little bit higher, but not much higher than 0.5 in some instances. That depends on the porosity and the density of the soil and how the grain size and all this. Okay, but again, what the radars or the scatterometers are measuring is basically changes in the reflectivity. And here you have examples. Okay, this is one single pass, okay, over the Iberian Peninsula made with Sentinel-1, okay, and then it takes 6 passes, okay, which is the revisit time of the Sentinel family, okay, until you get the full coverage of the Iberian Peninsula. So in most cases, also 6 days is not enough, okay, to map the soil moisture. And basically, the minimum requirement that was set for the ESA SMOS mission was once every 3 days, but then talking to the people would like to have actually twice per day at least, okay? But this is the best that can be done today. Again, as you have seen, everything that we are seeing so far are indices or indirect proxies of soil moisture. And more recently, okay, we have seen this progress or widespread of GNSS reflectometry. GNSS reflectometry, it's actually like a multi-static radar or scatterometer or altimeter, because it can be used for a number of applications, in which we pick the signals of satellite navigation systems. It can be GPS, Galileo, GLONASS, Beidou, or other augmentation systems. And then we have our receivers, typically in a LEO orbit, that pick the direct signal, which is transmitted at right-hand circular polarization, and then the reflected signal that in the reflection process, okay, it passes from right into left circular polarization, most of it, not completely. There is still a remnant in right-hand circular polarization, and then you can conduct polarimetric studies, okay? But the two main applications the first one is reflectometry, okay, in which basically we compare the power of the reflected signal divided by the power of the direct signal. Of course, with all the compensation effects for the different propagation paths, for the differences in the antenna patterns, and so on. And if we are able also to measure the difference in the time delay, and we know the geometry, we can also infer information on the height. So it's basically a passive, because we are not transmitting altimeter, a passive reflectometer, again, because we are not transmitting. And actually, we will not get just one point, but we will get as many points over the surface as reflections from the signals that these navigation satellites are transmitting, okay, our receiver can track. So our receiver that is more powerful will be able to track more simultaneous reflections, and we will have more tracks, okay, on the ground. It's not a full swath that this type of instruments measure, but just lines okay, parallel, more or less parallel to the subsatellite point. Okay, and now I'm going to come into the field of microwave radiometry, which was actually the first tests were performing the Skylab in the 1973. Okay, and they show the potential of this technique to measure soil moisture. Unfortunately, at that time, the resolution of the antenna that was put on board the Skylab, if I'm not wrong, it was about 1,200 kilometers. So you see, this is even larger than the full Iberian Peninsula that I put in the previous maps. Okay, so it was kind of useless. But the changes that were detected, depending on which region of the globe it was looking at, demonstrate the potential of this technique. So if before I show you we were measuring in the visible and near infrared part or in the thermal infrared part, etc. Now we go into the microwaves, okay? At a frequency of 1.4 gigahertz and a wavelength of 21 centimeters. So basically about the size of my hand. Okay, and what does a microwave radiometer measure? A microwave radiometer measures basically noise. It measures the thermal noise, very similar as when we have a radio receiver that is tuned into a band where nobody is transmitting. So what do we listen? We listen to a noise that is like, okay? This noise has two contributions, one that is being picked by the antenna and the other is the noise that is internally generated in the receiver itself, okay? But the contribution coming from the antenna, it turns to be related, of course, to the incidence angle or the observation angle, the polarization of the antenna, the land surface temperature, the roughness, and notably, okay, the soil moisture. So here you have a plot of the emissivity as a function of the incidence angle. These families of curves that go by pairs, this is the emissivity at vertical polarization as a function of the incidence angle. This one is at horizontal polarization, and this is for water. So you see, there is a difference between the two, okay? When we go to land, loamy soil that is about 25% in volumetric soil moisture, so 0.25, what you see, okay, at vertical polarization is like this, horizontal is like that, and you see that the emissivity, okay, this parameter here, that we will be multiplying by the land surface temperature to get the brightness temperature, and I will come back to this later in a little bit more detail, because this magnitude is proportional to the amount of noise that our radiometer is capturing, okay? You see it's higher than if the radiometer is pointing towards the ocean. But if the soil is not wet, it's dry, then the emissivity goes high. And this is what we are seeing here. These are actually two of the first orbits of SMOS. Okay, SMOS is this mission from the European Space Agency. Okay, and this is basically an ascending pass and a descending pass over South America. And you see, this is dark blue. Then you see also dark blue. Actually, this is the Amazon River. So water, we see less brightness temperature, we receive less noise. We also see less antenna temperature in the Pampas because it was very humid at that time. A little bit drier, then the temperature becomes higher, the brightness temperature. And then in this region here, which is the Amazon rainforest, okay, the soil is very wet. It is true, but there is a very, very dense vegetation, and the vegetation also impacts and actually attenuates the signal coming from the ground and then makes the emissivity go up. I will come to that in the subsequent slides, but I wanted to illustrate in a graphical manner what a microwave radiometer measures and how it looks like with real data from space. And last but not least, let me see if I can okay? There are other indirect ways, okay, to measure the amount of water. And this is really very subtle, okay? Are changes anomalies in the gravity field. So what you are seeing here are measures of the terrestrial water storage anomalies in centimeters of water. Okay, this is a mission. This is the GRACE mission that basically is two satellites that are measuring their distance very precisely with laser retroreflectors. And when the gravity is higher, then the first satellite accelerates, the distance between the two increases, and that allows to perform very, very precise measurements of the gravity field of the Earth. So when there is lots of of water accumulated in the soil and subsoil, it can be in the canopy, okay? In rivers and lake, so on the top of the surface, soil moisture in the top 5 centimeters, or underground water, okay? Or of course, in some regions, it can be ice, okay, or snow. This increases the gravity field, and that can provide a proxy, okay, of the amount of water that is stored overall. Okay, of course, the resolution is very coarse. We are talking now about hundreds of kilometers, but this can provide really very interesting patterns to see long-time evolutions of deficit or excess of water underground. So now going to the mapping of soil moisture, okay, with microwave radiometry from coarse to high resolution maps. As I said before, we have our microwave radiometer. It has an antenna, okay? And this antenna, I don't know your background, but an antenna basically receives most of the radiation from what we call the main lobe in blue color, but it can also pick radiation from the side lobes SL, okay, in red. So basically, the first thing is this amount of noise. Recall that the radiometer is like a radio, okay, and we measure the volume of this noise, no? This noise that looks like this, okay. We measure the intensity, the volume of this noise. So we not only have to remove the contribution of the noise that is generated internally in the receiver, because imagine that we disconnect the antenna and we still listen to the noise. So we need to subtract this contribution, but we need also to subtract the contribution from the side lobes, okay, to get the information from the main lobe. Okay, if we do that with a real aperture antenna, like in a Skylab, okay, the resolution was really, really poor, more than 1,000 kilometers. But if you want to have a decent, and by decent I would say even tenths of kilometers, then you end up with an antenna that is about tens of meters, 20 meters, okay, to get the order of magnitude. So because the antenna resolution is determined by the spatial resolution is determined by the antenna footprint, and the wavelength is very long, 21 centimeters, we need really large antennas, okay? And not only that, if we want to form an image, we need to scan this antenna to point into different directions. And that basically was what prevented for more than 2 decades to perform these measurements from space. Because first we were not able to make such large antennas, and later on, even though these antennas were developed for communication systems, we were not able to scan a 20-meter dish antenna. And this is how ESA, the European Space Agency, at the beginning of the 90s, came up with this concept, which is actually it was developed first in radio astronomy. Okay, so the very large array in Socorro. Actually, it's an array of antennas following a Y-shaped structure. Okay, but in this case, each of the antennas in the VLA, it's a big radio telescope. Here, it is a patch antenna. As you can see, there are 69 of these antenna elements. And a synthetic aperture radiometer, as opposed to a real aperture radiometer like this, is not measuring the power collected by the antenna. But what it does, it measures all the cross correlations between the different signals. So imagine if we have 69 antenna elements, in principle, we can perform 69 times 68 cross correlations. Actually, we can save half of them, okay, because some of the mathematical properties, but still 69 times 68 divided by 2, we are talking about thousands of complex cross correlations, okay? Still, this technique was found to be more efficient or feasible than the previous one. Because this structure, as we'll see, the image that is formed with an instrument like this, you don't have to move the antenna. The antenna has to be static, and instead of getting a point-like image, and then you move the array to point in different directions, you get the whole image at a time. It's like a camera, okay? But a camera that works at a wavelength of 21 centimeters. Okay, still, even though these arms are 4.5 meters long, so you can imagine the size of the antenna, the spatial resolution is quite coarse. It's about 50 kilometers, which basically it's okay for climate applications, but is not useful for agricultural applications. So how do we pass from this coarse resolution, 50 kilometers, into a much better resolution? And actually, I'm going to spoil myself, but now we are down to 60 meters, and in some cases, we have gone down to 20 meters. The first thing is basically to make some assumptions, is that some of the processes that occur at 50 kilometer scale are the same ones that occur at a lower scale. This is true up to the point in which basically in your footprint, you no longer see, for example, many trees, but you start seeing, okay, a tree and then a piece of bare soil and then another tree. As long as you still have a relatively large number of trees in the footprint, that can be 20 meters or 60 meters, okay, things hold. So what we have is that we set a linear regression model, okay, at the beginning with soil moisture as a function of the LST, okay, the NDVI, because we see that NDVI and the land surface temperature, as they were used as proxies for the soil moisture, we want to bring this information back, okay, into the soil moisture. Why? Because we can get LST or NDVI with a much higher resolution that we can with the brightness temperatures at horizontal and at vertical polarization. And actually, one of the things that we found is that osmosis measuring with the full range of incidence angles, but with three angles, okay, at horizontal polarization and vertical polarization, it is enough. So here we have our reference soil moisture in a grid of 25 kilometers. Okay, these are the brightness temperatures, land surface temperature, and the NDVI. We will be getting this LST either from satellite data or from models like the predictions from ECNWF, NDVI from MODIS, or nowadays from Sentinel-3 at 300-meter resolution. Okay, and the brightness temperatures, again, I said the spatial resolution is about 50 kilometers, but the products are provided in a grid of 25 kilometers. And these are the three incidence angles that we are working with. Okay, so this is basically the result. So basically what we did before is basically to make this fit. Okay, that's a different story in how we make this fit. But once we have it, okay, you see that the correlation is pretty high, depending on which type of network we are. And Remedios is in Salamanca. As I presented before, the correlation is much higher. In other places, okay, this is in Romania, okay, where it is wetter, the correlation is a little bit worse, especially because it tends to be more cloudy, and the variations of LST, okay, you are not bringing that much information into the soil moisture. Okay, and here you see the in situ and how it follows at different scales. Okay, there is a bias. Actually, it's you see that all the points tend to be a little bit lower, but the trend is captured relatively well. Okay, and the work that we are doing now, that is the one that allows us to go to the limit, is using feed-forward neural networks. This is the type of source of data that we use. In here, we include precipitation, LST as well, the reflectance from the Sentinel, not necessarily the NDVI, but the reflectance themselves. We also include the delay, the a digital elevation map and the slope, and also the orientation of the slope, and parameters related to the soil structure, okay, so clay and sand fractions. We train this machine learning model, okay, with 80% of the data. We test with 20% of the data, okay. Again, the training area has been, in this case, the Iberian Peninsula, and then we validate in this Remedus area in Salamanca. And here you have the performance assessment as compared to the ESA CCI soil moisture values. And here you have how it looks like. This is the original product from ESA CCI, and this is the estimated soil moisture map at 60-meter resolution. So now you can see with a lot more detail, even the mountains, the valleys of the rivers, etc., that are wetter, etc. Okay, so this is what we do at the Barcelona ESMOS Expert Center, BEC. Okay, that is a joint venture between the Institute of Marine Sciences, from where one of the two PIs of ESMOS was, and UPC. So we produce ocean and land products from ESMOS from level 0 to level 4 for a number of different applications. And as I said, we can pass from the native resolution, 50 kilometers, level 2 soil moisture products, down to 60-meter resolution at level 4. So here you see in this animation, it passes from the visible image that you can see in Google Earth into the soil moisture that you can downscale. And again, you can see visually that wherever you have vegetation, actually the soil moisture is higher. Okay, that's why many people were using NDVI as an indirect proxy of soil moisture. Okay, so some applications that I wanted to show quickly. The shots in the Algeria region. Okay, these are salt lakes that sometimes they are completely dry, and sometimes here you see the map with 300-meter resolution. Sometimes they get wet. Okay, and well, even there are boats, etc. So this is in this part of between Tunis and Algeria. Okay, and this is another example of some developments around in Egypt. Okay, in this East Owenite land reclamation agricultural project. Okay, here you see the evolution as a function of time. These are images from Landsat and Sentinel-2. So you see how it has evolved from the year 2001 until present. These are actually each of these little dots that you see here. It's one of these pivots, okay, that are used for irrigation. Okay. Here you see again the same thing. This is ESMOS downscale. CCI soil moisture downscale at 60 meters. Okay, so here you see the final piece. Then if we zoom in this little rectangle here, we get this image. If we still zoom in, okay, this rectangle here becomes this one. And this is each of these individual pivots. Okay, and you can see the size of these pivots because it's about 1 kilometer. And then you see how the soil moisture varies within each of these individual pivots. So I think this is useful information for when you want to manage the irrigation in these regions, and of course in Spain as well. But in regions where the water is more scarce, I think this is more important. Here you see the evolution, and finally, this is what you will see, okay, with an RGB image from Sentinel-2. Okay. Another example, now it's at 1 kilometer. You can use that to do flood monitoring in the Algeria region and Tunis, and this is in the year 2021. Okay, and I want to show you an example. Let me see. Okay, this is animation that Dr. Miriam Pablos and myself created that corresponds to the floodings that occur in the UAE in July 2022, Fujairah, and there were some fronts. So here you will see the rain rate, okay, and you will see, of course, you have this at a much higher temporal resolution, and ESMOS passes once every 3 days. So here you have in the top right corner the date. Okay, so that's August the 5th August 8th, and you see the soil moisture patterns that you see in the country. Okay, I will pass it again because the floodings occurred before. Let me see if I can. Okay, now you will see the rain front passing and then getting all the floods over here at the end of July. Now, okay, and then days later it gets dry, like now, that's August the 3rd, okay, and then you will see other fronts, okay, creating soil moisture, okay, that it's clearly visible even in desert, and then after the rain, the soil moisture remains, and then a few days later it evaporates. Okay, and now GNSS-R, quickly, I commented already this. In GNSS-R, what we measure is the reflectivity as the ratio of these two powers, and the reflectivity is a function of the soil moisture, the surface roughness height, and the vegetation optical depth. So the sensitivity to soil moisture is extremely non-linear. Okay, so beware when you see an algorithm that is using linear relationships for relating the changes in the reflectivity with the soil moisture, because they are inherent limitations. They only work in small ranges of soil moisture, either for dry regions or for wetter regions, but they cannot cover the full soil moisture range. Okay, in any case, the sensitivity is pretty decent because we have about 10 dB changes, okay, when the soil moisture changes from 0 to 0.45, and actually these instruments can measure the reflectivity with a fraction of a dB. The sensitivity, unfortunately, as with any active system, okay, because this is an active system, but using the signals that are transmitted by others, the sensitivity to roughness is also high. And as you can see, I mean, we can lose a significant amount of power, okay? So this is the power, peak power in dB watts, okay, just when the surface roughness increases. So actually, this is the most difficult problem when you want to retrieve soil moisture from GNSS-R data, the compensation of the surface roughness effects. And to do that, you can use multi-frequency measurements, for example, at L1 and L5. And then you also have the effect of vegetation. Vegetation attenuates the signal. The signal, when it goes down and then it goes up, the signal gets attenuated, and therefore you receive less power. So you need to compensate for that as well. And to do that, again, either you use multi-frequency measurements or you use other proxies like the NDVI. Okay, just to illustrate, these are examples of instruments from us flying over Australia. Okay, because it's much easier to do experiments over there in the plane than it is in Europe or in the US. And here you see, for example, taking off from Melbourne Airport, okay, going to this island and then heading towards the Janko area, okay, for the where Professor Jeff Walker has a test area in Genco. And here you see that over the water, the reflectivity is much different than over land. And you see here, for example, peaks of higher reflectivity that actually correspond to water bodies. And in particular, for example, this is already in the Janko area. This is an irrigation channel, and you see, okay, the high reflectivity that you get when the reflection point crosses the water bodies. You also see the changes in different agricultural fields depending on if they are harvested or irrigated or not. Okay, and this is very important because the resolution that you can achieve, even from a plane, from a satellite, if the reflection is coherent, goes from 300 to 400 meters from space using an antenna that is the size of an A4 piece of paper, which is a 6-unit CubeSat. Because actually, the spatial resolution does not depend on the antenna size. The antenna size determines the signal-to-noise ratio that you receive, but the spatial resolution does not depend on the antenna size. Okay, other examples of use of data. This is from NASA Cygnus mission. It's a constellation of 8 microsatellites, and they have been able to see for the first time, because this was never seen before with this level of detail, okay, all the tributaries for the Amazon or in the Congo River, because of the forward scattering, okay? It's not like in a radar, even a synthetic aperture one, where it is back scattering configuration. And in back scattering, you are more sensitive to the volume scattering. That is what occurs in the vegetation. But in the forward scattering, you are more sensitive to this coherent component that passes through the vegetation, reflects on the water underneath, and then goes up. So you see, you can make maps of areas that are flooded even under a very, very dense vegetation. Other applications, okay, we can use the attenuation of the GNSS signals and comparing from a tower and underneath, okay? And you see this is the NDVI, the green dots, and this is the signal that you're receiving with your GNSS receiver. And you see that they are inversely correlated. Why? Because the greener the vegetation is, the higher, the more water, okay, the larger the attenuation. And what is important is that the attenuation that you see here is, in this case, in this forest in the north of Catalonia, is about 10 dB, okay? You can relate this, okay, with the amount of water that is contained in the vegetation. Okay, and this is another example of a work that we published recently, where we see this VOD, vegetation optical depth, how it relates to the vegetation water content, okay, in the Amazon, okay, and we can even see the daily variation. This is the reflectivity, change in the reflectivity, and this is the change in the vegetation water content on a sub-daily basis, nearly every hour in the Amazon. Okay, and very quickly, because I'm running a bit out of time, an application that we are doing in some fields in the western part of Catalonia. Actually, it's kind of, I was going to say funny, but actually it's not funny. It's we had to ask for an extension because we passed until basically a couple of months ago the most severe droughts in 150 years in the country, okay, with almost not a single raindrop in 3 years. So they even cut the irrigation in all the fields, and we say, okay, we need 1 more year to see if we can do it, and we got it. And actually, since September, I mean, we have getting lots of rain, as probably you have seen in the news in Valencia last week, in Barcelona this week. Okay, so it's a bit surprising. But in any case, we want, because this problem of droughts is going to happen again and again, we wanted to optimize the use of water resources, and we are worried about the water that is in the subsoil, which is from where the plants took the water basically to grow and to produce the fruits, okay? Because the problem here is about food security. So this is Barcelona area. Here is where we have our 2 fields, okay? Actually, this corresponds to the place where I showed you the NDVI before. And what we have is a network of 20 probes that measure in depth, okay? And also we have meteo stations, we have satellite data providing NDVI, land surface temperature, the soil moisture downscale from SMOS, etc., evapotranspiration maps. I don't know if I say already meteo stations. Okay, everything is interconnected, okay, through a network of IoT sensors. We receive the data, and basically we develop a model. Actually, it's a neural network architecture. I'm not a big fan of using artificial intelligence. I prefer to understand what is happening, okay? But still, the problem is complex enough in order to model with a simple formula. So we have a neural network approach in which basically we train. We have 2 hidden layers, okay, and we estimate basically the soil moisture up to 5 depths. And I will show you why, because we encounter that even though we measure the soil moisture down to 115 centimeters depth, actually there are like 2 regimes. Okay, this is the correlation matrix of all the variables, atmospheric variables, etc. And here is soil moisture probes from 5 centimeters up to 115 centimeters. And you see there is correlation up to about, depending on the place where the probe is, we can see it up to 65 or 45 centimeters. Okay, beyond that, it has its own life. The values of the soil moisture, they are correlated among them, okay, but they are uncorrelated, okay, or very poorly correlated with the soil moisture at shallower depths. Okay, so a few examples of the estimation in orange color. Blue is the real data as measured by the probes. So this is probe 1 in this field, okay, at different depths from 5 to 45 centimeters. Same thing for another of the probes, very different behavior, even though the two fields are very close. The structure of the terrain is totally different. You see here, for example, it gets almost saturated all the time. And then to conclude, I have tried to present the different techniques, okay, that are used to map or infer proxies of soil moisture, okay? Even from the NDVI, even though it is not soil moisture what it measures, but talking to the farmers in the region, this is what they use, basically because it's free and they can get them in their phone and they can see if one of the pivots has some of the aspersors or water irrigators is blocked or there is a problem, etc. They realize immediately because they see that the vegetation is not growing properly. Okay, so the NDVI goes down. It's not soil moisture, but it's used. Okay, I
Sorry.
have presented these algorithms. I'm finishing. Okay, the potential of GNSS is there because GNSS, there are no replacements for either SMOS or SMAP. So probably we will have to rely on GNSS. And I think that all this data can be used for make a better use of the water resources in an environment where the climate is changing and we are going to pass from long and severe droughts into flooding periods like we are seeing here in Spain. So sorry for being a bit late. Thank you for your attention. If you have any questions, I will be more than happy to answer.